Okay, this is problem 5.57, and in this problem we're given the threshold voltage Vt 0.9 volts and the device transconductance of 1.5 milliamperes per volt squared. And these parameters here, they are both common to both MOSFETs that we have and MOS that we have here in this circuit. Now, if we look at this circuit, there's some information that we can get from it. So first, this is the drain of the first transistor. Then here we have the source of the first transistor and the drain of the second one. Here is the source of the second transistor. And then here we have the gate, and here we have the gate of the second and the first transistor. Okay, so in this particular problem we need to define V1 and V2. Okay, now if we look at the gate of the first transistor right here, we know that VG1 is equals to 2.5 volts. Okay, that's what we have because those 2.5 are connected directly to the gate. We also know that VD1 is equals to 5 volts. And if we look at this second transistor, we know that VG2, so the gate voltage, is 0 volts because it's grounded, right? So here it's grounded. Now, because the source and the drain, so the source from the first transistor is connected directly to the drain of the second transistor, we also know that VD2 is equals to VS1. And because we don't have currents flowing from the gate to the drain or the source, so those currents here, right, this one here is 0 and 0 amperes, and here is also 0 amperes. The current flowing here, here, and here, they are all the same. So we have a single ID here that is equals to IS1, ID2, IS2, ID1. So we have a single current ID. Okay. Now this current, and because it's all the same current, we can start analyzing this particular branch here at the source of the second transistor. And we can define ID, so we can define this ID in terms of 1 over half Kn V over drive squared, right? And we are assuming, I mean, it's not just this drain current here at the source, but it's the current that's flowing through all the drains and sources of this arrangement of transistor, right? And one thing is that we can define this drain current in terms of this, also in terms of V2 minus 2.5 divided by that 1k ohm, right? So let's just forget about this one first to not confuse you. So let's stick with this ID here. Now, how do we define so we define this ID here, right? And from this ID here, we can use this drain, the source current here, to isolate V2. And how can we do that? So we know that VGS2 is equals to VG2 minus VS2. And because the gate here is grounded, we know that this voltage here is 0. So in our case, VGS2 is equals to minus VS2, which in our case is equals to minus V2, right? Because it's the same potential here, right? So we have this equation here, and we also have this one here for ID. So now that we have that VGS2 is equals to minus V2 and that ID is also, it also depends on V2, we can use the saturation, the current, the drain current at the saturation mode to calculate this current here. So now we have ID equals 1/2 of Kn V over drive squared. And if you remember, ID we just defined as V2 plus 2.5 divided by 1K ohm, and that's equals to 1/2 Kn. Now what's V over drive? V over drive is VGS, in our case VGS2, right? So VGS2 minus VT squared. And we know that this VGS2 here is actually minus V2. So similar to the previous problems that we had, like a quadratic equation to solve, this one here is just the same case. Okay, so if we isolate V2 squared, V2 and the constant term and equate that equals to 0 from this equation here, okay, we get that 0.75 V2 squared plus 0.35 V2 minus 1.892 should be equals to 0. Okay, and if we solve this equation here using the same approach as before, we find a V21 that is equals to minus 1.8390 volts in a V22, so there are two solutions, right, because it's quadratic, two roots, so one is minus 1.839 and the other one is 1.3720. Now this one here, it's not allowed because it doesn't agree with the saturation condition, so it doesn't gives us the correct condition. And for V2 here equals to minus 1.83 volts, that's actually okay with the saturation condition. Okay, so we can calculate now VS1. Let me see. Now we can actually calculate the current ID, right? Because we just defined V2, so we have an equation for ID, and ID is actually V2 plus 2.5 divided by 1K ohm. And this gives us an ID that's equals to V2, so it's 2.5 minus 1.8390 divided by 1K ohm. And this gives us an ID that's equals to 0.66 milliamps. So now we found the value of ID. Now with this value of ID, we can calculate, for example, the V over drive of the first transistor, right? And for that we know, so for this one here, we know that V over drive is equals to the square root of 2 times ID. And remember, ID, even if we calculated this current here, right, it is the same all over these branches, right? Because this one here is 0 amperes, this one here is 0 amperes. So we can just isolate V overdrive in the equation for ID, the same equation that we used up there to actually define the value of ID here. But now we are analyzing for the first transistor. So this V overdrive 1 is 2 times ID divided by Kn. And this gives us a V overdrive 1 that is equals to 2 times 0.66 milliamperes divided by Kn, which is 1.5 milliamperes per square volts. So this V overdrive here, 1, is 0.9381. And with this V overdrive, we can actually calculate VGS1 now. So VGS1 is equals to V overdrive 1 plus the threshold voltage. And this gives us VG1 minus VS1 equals to V overdrive 1 plus the threshold voltage. Now, if you remember, this VG1 here is actually those 2.5 volts here. So we can isolate, so it's 2.5 minus VS1 equals to overdrive voltage 0.9381 plus the threshold voltage. And the threshold voltage for this particular problem is, for those particular transistors, are 0.9 volts. Okay, so VS1 is equals to 2.5 minus 0.9381 minus 0.9. And this gives us VS1 equals to 0.66 volts. And now if you remember VS1, which is this potential here, right here, let me show you the entire circuit. This potential here is actually equals to V1. So V1 is equals to 0.66 volts. So in summary, we started with this branch here, and then we figure out the value of ID. And because ID is the same flowing all over the drain and sources of our transistors, we could figure out this voltage VS1 here. Okay. Now for part B, so let me go down here. Let me pick part B. So for part B, we have a different circuit, but the parameters of the transistors, they are kept the same. So we still have VT here, that's 0.9, and the device transconductance, that is 1.5 milliamps per volt squared. Now if we look at this circuit now, we know that VG1, so this gate voltage here and this drain voltage here, and V3, they are all the same, right? Because they are all connected to this node here. So VG1 is equals to VD1, and that's equals to V3. For the second transistor, we have a similar thing here. So this is a common node, right? So we have the drain here, gate, and V4. So VD2 is equals to VD2 that's equals to V4. So those are the two equations that we have. And again, because there is no current, so there is no current flowing here, right? This is 0 amperes, this is also 0 amperes, there's no current flowing at the gate. This current here is the same as this current here, which is the same as this current here. And that's basically ID, right? So they're all ID. And we can calculate ID, so this is ID, this is also ID, and this is also ID. Now if we look at this particular branch here, we can define the current, the drain current here, or the source, right? But it's just the same current, using Ohm's law. And that equals to V5 minus 0, because it's grounded here, divided by 1K. So this gives us V5 divided by 1K. Okay, that's the equation for ID based on the analysis of this branch here at the bottom. Now we can write an equation again for VGS2. So VGS2, that is equals to V4 minus V5, right? Because it's this potential difference here. So exactly here we have V4, and exactly here we have V5. So that's an equation. VGS2 is equals to V4 minus V5. Now if we go up there, we can write a similar equation for VGS1, right? So VGS1 here, right? VGS1 is equals to V3, right? The potential here minus the potential here, which is V4. Correct? So those are two equations that we have. So we still have like 1, 2, 3 equations here, and 3 unknowns, sorry. And we still need to simplify the equations to be in order to be able to find out some quantities in this circuit. So if we now look at this branch here, we can write that this 5 minus V3, right? This potential difference here, which is 5 minus V3, is equals to ID, which is the current here, right? This current here flowing through the 1K times 1K. And we know that ID, this one here, is actually V5 over 1K. So if we substitute this one here, we get another equation that relates V3 with V5. So 5 minus V3 is equals to V5 divided by 1K times 1K. Those two, they cancel. And then we get an equation that basically tells us that V5 is equals to 5 minus V3. Now we can substitute this one back in VGS2. Right, substituting this term here. So the equation that we get is then VGS2 equals to V4 plus, so it's minus V5, so it's plus V3 minus 5 volts. Okay, and if we write again VGS1 equals to V3 minus V4, we have a set of equations that basically depend, so we have two equations that depend only on V3 and V4. Okay, now we can use the current equation, so ID equals 1/2 of Kn V over drive squared, to calculate the drain current flowing here, right? And to calculate the drain current flowing here, because they are all the same, right? Remember that they are all the same current. So we can either use VGS2 or VGS1 to calculate the same current, and then we can basically make them equal, right? So if we substitute V over drive here using VGS1 and VGS2, we get that 1 over 2 Kn V over drive 1 squared is equals to 1/2 Kn V over drive 2 squared, right? Because it's the same current. So basically this one simplifies here, this one simplifies here, and then we get that V over drive 1 is equals to V over drive 2 for this particular circuit, right? So V over drive 1 is the same as VGS1 minus VT equals to VGS2 minus VT. And this basically gives us that VGS1 is equals to VGS2. So we can make this one here equals to this one here. And this gives us V4 plus V3 minus 5 equals to V3 minus V4, which is the same as 2V4 equals to 5, which gives us V4 equals to 5 divided by 2, that is 2.5 volts. Okay, so we find out the first unknown here, which is V4, 2.5. And there's some symmetry in this circuit here that would allow us to define V4 equals to 2.5 directly, but that's basically the equations that we have to take from this circuit to get this result here, that is 2.5. Okay, so V4 is equals to 2.5. Now we can equate, so because we know V4, right, we can now equate ID using VGS2 again, because we can calculate VGS2, right? Let me go up here. So VGS2 we can calculate, we still don't know V3, but we can use VGS2 to calculate another ID. So we know that, remember, ID is equals 1/2 to Kn V over drive 2 squared. We know that ID is V5 divided by 1K. We defined that before at the beginning of the solution. And this is equals to 1/2, 1.5, 1.5, 1.5. Sorry about that. So let me go back here. So we have ID equals to 1/2 Kn V over drive 2 squared, and ID is V5 divided by 1K, and that's equals to 1 over 2 times 1.5 milliamp square volts VGS2 minus VT squared. Okay, and we can basically write VGS2 in terms of V5, right? Because I think we have an equation for that. So let me go up here. this one here, because we know V4, right? So VGS2, remember that VGS2 is equal to V4 minus V5, and that's equals to 2.5 minus V5. So we can substitute this one here up here. And again, we are going to have a quadratic formula, where we have to use a quadratic formula to solve this quadratic equation. So if we substitute this one here in VGS2, we can isolate V5, right? V5 here and here. And the quadratic equation that we have is 0.75 V5 squared minus 3.4 V5 plus 1.92 equals to 0. And this gives us two solutions for V5. So we'll call V5 1, that's 3.87 volts, and V5 2 equals to 0.66 volts. Okay, so one thing here is that we have to pick this one, because this one here gives us the condition that VGS2 is actually greater than 0.7. Because if we take this one here, okay, VGS2 is equals to 2.5 minus V5. So it's minus 3.87. And as you see, this result here is negative, right? So it's something negative here. So I don't have the exact value here, but it would be 1.30 minus 1.37. That's less than VT, right? And this one here, it doesn't allow us to use the equation for ID here in the saturation region. So we need to pick this one here, 0.66, because then VGS2 is going to be 2.5 minus 0.66. And this gives us something that is greater than VT, okay? So that's the reason we are picking V5 to equals to 0.66 volts. And now we can actually calculate the value of ID. So ID is equals to 0.66, right? It's just V5 divided by 1K. And that's 0.66 milliamps. So we got ID, we got V4, we got V5. We still need to calculate V3, okay? And for V3, we know that there's one of the equations that V3 is equals to VGS1 plus V4. That's one of the equations that we derived at the beginning of the part B. So this V3 here is equals to VG1 minus VS1 plus V4. Now VG1, let me see, VG1, oh yeah, we can calculate. So let me just erase this part here. We know that V3 is going to be equal, so what's VGS1 is V over drive 1, right, plus VT plus V4. What's V over drive 1? V over drive 1 is equals to the square root of 2 times ID divided by the device transconductance. And V01 is equals to square root of 2 times 0.66 milliamps divided by 1.5 milliamp per square volts. And this gives us 0.9381. So we can substitute, so we know V over drive 1, we know Vt, we also know V4. So V3 is equals to those 0.9381 plus Vt, which is 0.9, plus V4, that is 2.5. So this gives us a V3 that's equals to 4.33 volts. Okay, and it actually agrees with the condition that if we know ID, right, we just calculated ID here, and we are trying to define V3. If we take this potential here, there's another way to check our answer, is that the voltage across that 1K is equals to those 5 volts, right, up there, so 5 volts minus V3, and that's equals to ID times those 1K. So if we take minus V3 equals to minus 5 plus ID times 1K, we get that V3 is equals to 5 minus 0.66, remember the value of ID that we just calculated up there, so this one here, 0.66. So let me go back here, 0.66 milliamps times 1K ohms, right? This gives us a V3 that's 5 minus 0.66, and this V3 here is 4.34 if you want to make more complete, right? But it's 4.33 up here, or you can round to 4.34. And that's it for this problem.